welcome to Two Projects. In this video, we are going to explain the project Research on Road Object Detection Model based on YOLOv4 of Autonomous Vehicle. Before diving into the execution, let me give you an overview of the project. So, what are these autonomous vehicles? So, autonomous vehicles are vehicles which do not need human intervention or human help. So, road object detection is very important for autonomous vehicles as it enables them to perceive and understand their surroundings, similar to how human drivers do. This capability is important for ensuring the safety of passengers and pedestrians, optimizing driving efficiency, managing traffic flow, and providing a seamless user experience. In the past, detecting objects on roads relied on manually crafted rules and features, but these methods struggled to cope with the complexities of the real world scenarios. Variations in lighting conditions, occlusions, and diverse object shapes and sizes posed challenges for traditional approaches, limiting their effectiveness in practical applications. So, the project focuses on leveraging advanced deep learning techniques, particularly convolutional neural networks, that is CNNs, to develop a robust road object detection model. Specifically, the project uses YOLO, that is, You Only Look Once, a state of the art deep learning architecture known for its accuracy and efficiency in real time object detection tasks. By harnessing the power of YOLO, the project aims to overcome the limitations of traditional methods and create a highly accurate and adaptable solution tailored for autonomous vehicles. So, we will be employing YOLO models in this project for object detection. Now, we'll look at the workflow. So, the dataset used in this project is composed of images and annotations gathered from various sources including the KAIST, UDST, and Pascal datasets. So these datasets offer a diverse range of road scenarios, providing ample training and evaluation data for the object detection models. The images depict different road conditions, environments, and objects commonly encountered in real world driving scenarios. Coming to the workflow, the first step involves extracting image data from the dataset for further processing and analysis. This involves accessing the images stored in the dataset and loading them into the computational environment for manipulation. And various transformations are applied to the images to prepare them for input into the object detection models. These transformations include resizing the images into a standardized format, normalization to ensure consistent pixel values across images, and augmentation techniques to introduce variability into the dataset. So, augmentation techniques such as rotation, translation, flipping, and changes in brightness or contrast are employed to generate additional training samples, enhancing the model's ability to generalize and perform well in diverse road scenarios. So we will be training the models on original dataset from different angles so that the models can generalize well to different conditions and situations. So after these pre-processing steps, different variations of YOLO, that is You Only Look Once architecture, are implemented and evaluated for their performance in object detection for autonomous vehicles. This includes variants such as YOLO V4, YOLO V4 Tiny, MobileNet V2 YOLO, YOLO V7 Tiny, and others. Each variant is trained and tested using the prepared dataset to assess its accuracy, speed, and suitability for applications in autonomous driving scenarios. And the performance of each YOLO variant is evaluated based on metrics such as precision recall and mean average precision, that is MAP, to select the best performing model. So this is what happens in this project. Overall, the project aims to develop a reliable road object detection model for autonomous vehicles, benefiting manufacturers, transportation authorities, and the general public. By ensuring high accuracy and performance, the model enhances safety and efficiency on the roads. Manufacturers can build safer vehicles, authorities can manage traffic better, and the public enjoys safer roads and improved transportation systems. Ultimately, the project contributes to safer roads and a smoother transportation experience for everyone involved. Now we'll look at the software and hardware requirements to execute this project. Hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software requirements are application needed is Anaconda, primary language required is Python, front-end framework needed is Flask, backend framework needed is Jupyter Notebook, database required is SQLite 3, and front-end technologies required are HTML, CSS, JavaScript, and Bootstrap 4. Now we look at the algorithms built. So in the base paper, author has proposed MobileNet V2 is based on YOLOv4, and he compared this proposed model with YOLOv4, YOLOv4 Tiny, MobileNet V2 based on YOLOv4, YOLOv7 Tiny, and YOLOv8. And he concluded that MobileNet V2S based on YOLOv4 has outperformed all other models. For improved performance, we are proposing YOLO V8N and YOLO V5X6 in this project. We will be building all these models and will compare their performance using different performance metrics like precision recall and MAP scores, and will select the best performing model among them for object detection. So after doing all this, we have observed that YOLO V5X6 has outperformed all other models. So we have deployed YOLO V5X6 into the Flask web application. Now we'll understand about the YOLO V5X6 in brief. First, we'll understand about YOLO, that is, you only look once. So YOLO is a computer vision object detection algorithm that quickly identifies objects in images by splitting the input image into a grid and simultaneously predicting bounding boxes and class probabilities. Unlike traditional methods, YOLO processes the image just once, making it extremely fast. It predicts multiple bounding boxes and their associated class probabilities for each grid cell, and then removes redundant detections using non maximum suppression. This results in a final list of detected objects along with their bounding boxes and probabilities. So these are different versions of YOLO. Coming to YOLO V5X6, it is a variant of the YOLO V5 object detection model designed to strike a balance between accuracy and speed. With around 2.4 million parameters, it offers good precision and recall while maintaining efficient processing speed. Its architecture is optimized to handle 1280 by 1280 input images, making it suitable for real-time object detection tasks. YOLO V5X6 is chosen for this project due to its ability to provide accurate and fast detection, making it well suited for identifying objects in images. Its medium sized architecture and optimized parameters allow for efficient processing of images while maintaining high detection accuracy, aligning perfectly with the project's objective of enhancing object detection capabilities in complex environments. So, this is about YOLO V5X6. So, now we'll look at the execution. We will be executing the project using Flask web application. So before that, first we need to open the code folder which contains the project source code files. So this is the code folder and these are the contents I have in the code folder. So these are the three datasets we are using. Cased, Pascal, and Udacity. So the Cased and Udacity data sets offer real world driving scenes captured from vehicle mounted cameras, while the Pascal data set provides images of various objects. So these data sets help train the model to detect objects accurately in different driving environments. So now I'm opening Cased folder. Here we can see I have three separate folders for YOLOv5, YOLOv7 and YOLOv8. I'm opening YOLOv5 folder. So we can see I have test, train and valid folders here. Each serves a distinct purpose in the training and evaluation of the YOLO models. So train images in the train folder are used for teaching the models to recognize objects. Test images in the test folder evaluate how well the models perform on unseen data, and validation images help fine tune the models for optimal performance. So I'm opening train folder now. Here we can see I have two subsets again, images and labels. I'm opening images folder. So these are the images I have in the cased dataset. And in labels folder, I have annotation files. So each label file or annotation file corresponds to an image file in the images folder, providing details about the objects, locations, and classes within the image. So this annotation file corresponds to this image. In the same way, this annotation file corresponds to this image. Similarly, each annotation file corresponds to an image in the images folder. So these label files often follow YOLO format, where each line, this is the line, this is another line. So each line represents a detected object. We can see here we have four lines. That means in this image there are four objects detected. And each line specifies object class index. The first column is the class index, followed by its bounding box coordinates. These are the bounding box coordinates normalized to the image dimensions. This is the x limit, this is the y limit, this is the width, and this is the height. So in the same way, I have class index followed by the bounding box coordinates representing a object in the image in other files also. And each label file correspond to an image file in the images folder. So this is about the labels folder. So on these label files and images, we will be training the YOLOv5 models. So here we can see I have separate folders for YOLOv5, YOLOv7 and YOLOv8. Each folder contains the same images, but they are annotated differently because each YOLO version requires its own specific type of image annotations for training and testing the models effectively. Having separate folders like this helps keep the dataset organized and ensures that each version receives the correct annotations it needs to function properly. In the same way, I have separate folders for YOLOv5, YOLOv7, and YOLOv8 in Pascal and Udacity folders also. And inside these folders, I have train and valid sets. Train set is for training the models, and here validation set is for evaluating the model's performance. So I have images and label files here also. So this is about the dataset. And in sample folder also I have images from Cased, Pascal and Udacity on which we'll make the detections. This is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the train models. These are Jupyter source files, which contains a combination of code, graphs, and outputs all in one place. So Jupyter Notebook allows users to write and execute code in individual cells, making it a popular choice for data science. So these are respective Jupyter source files. And this is signup.db file. This file is the database file used to store user information. So it stores information like sign up details. So this is about the code folder. Now copy the path of the code folder from the address bar of the file explorer. This is the path. Copy it. Open Anaconda prompt. So here we can see it is locating it to the C drive, but we have the code folder in the D drive. So we have to change the drive here. For that, use the command D colon and hit the enter button. So we can see the drive location has been changed. Now we use the command cd followed by a space and paste the copied path of the code folder and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, local host, and the port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I usually prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. If we are new users, we have to register ourselves first. Fill in all these details and click on register button to sign up. And if we already have account, we can directly log in by clicking on the sign in link. So as I'm already a member, I'm clicking on this link. Here we have to give our credentials, username and password. I'm giving mine and click on login button. So it has redirected us to the detection page. So here we can see a detection link, click on it. As I mentioned earlier, we can execute the project using three different datasets, Pascal, Udacity, and Cased. First, we'll execute the project using Cased dataset, click on it. Now here we have to upload any image and the application will detect the cars from the image. Click on choose file button. From sample folder, as we are executing the project using Cased dataset, from Cased folder, we have to select any image. These are the test cases I have. I'm selecting the first image and click on open. The image has been loaded. Now click on upload button. So we can see the application has detected all the cars in the image. It has drawn a bounding box around the detected cars and we can see the label here. Beside the label, we can see a probability score telling us the confidence level of the application in labeling them as cars. Click on back, click on choose file. We'll try with this image. Select the image, click on open and click on upload. We can see the application has detected the cards. We can see the bounding boxes drawn. We can see the label and beside the label we can see the probability score. Click on choose file. We'll try with this image. We can see the cars detected. We'll try with this image. So these are all the cars detected. We can see the bounding boxes drawn around the detections. We can see the label and we can see the probability score telling us how confident the application is in classifying them as cars. Click on back, click on choose file. We'll try with this image. We'll try with this one. We can see the cars detected. We'll try with this image. We can see a truck detected here and we can see the cars detected. Click on back, click on choose file. We'll try with this image. We can see a truck detected and we can see the cars detected. So in this way, we have to upload image and the application will detect the vehicles in the image. Now we'll execute the project using Udacity dataset. Click on Udacity link. Now we have to upload images here again. It will detect different objects from the image. Click on choose file button. So this time from Udacity folder, we'll try uploading the first image. We can see the application has detected the cars in the image. It has drawn bounding boxes around the detections. It has labeled them as car and we can see the probability score beside the label telling us the confidence level of the application in detecting them as cars. Click on back, click on choose file. This time we'll upload this image. We can see the application has detected different objects. It has detected the cars. It has detected the traffic light red, traffic light red left. And beside the label, we can see the probability scores. Click on back, click on choose file. We'll try with this image. We can see the traffic lights detected, the cars detected. We can see the labels, car, traffic light green, and we can see the probability scores. Click on back, click on choose file. We'll try with this image. We can see biker, pedestrian, car, traffic lights detected. So we can see different objects being detected in a scene in the image, in the road. We can see the probability scores beside the label, telling us the confidence level of the application in detecting them. Click on back, click on choose file. We'll try with this image. Click on open. We can see the application has detected all the cars in the image. We'll try with this one. We can see the traffic light red, pedestrian, car detected. We'll try with this image. So we can see the detections here, traffic lights, cars. We can see the bounding boxes drawn. We can see the labels and we can see the probability scores. In the same way, we can upload any image from the test cases and can get the detections, the classifications, and the probability score. We'll try with one last image from this dataset. We'll try with this one. We can see all the cars detected. Click on back. Now we'll execute the project using Pascal dataset. Click on Pascal link. We have to upload images again. Click on choose file button. So this time from Pascal folder in the sample folder. So these are the test cases I have. I'm selecting this image and click on open. The image has been loaded. Now click on upload button. We can see the application has detected the person from the image. It has drawn a bounding box around the detected object. It has labeled it as person. And beside the label, we can see a probability score telling us the confidence level of the application in classifying it as person. Click on back. Click on choose file. We'll try with this image. We can see the application has detected the object. It has drawn a bounding box around the detected object and labeled it as TV monitor. And beside the label, we can see the probability score. We'll try with this one. We can see the application has detected the aeroplanes. We'll try with this one. We can see the application has detected the monitor. We'll try with this image. We can see the application has detected different objects. It has detected person, it has detected the bus, and it has detected the bicycle from the image. We can see the labels. We can see the bounding boxes drawn, and we can see the probability scores beside the labels telling us how confident the application is in classifying them into that particular class. Click on back, click on choose file. We'll try with this image. We can see the application has detected the car. We'll try with this image. Click on open. Click on upload button. We can see the application has detected the buses. We can see the bounding boxes drawn. We can see the label and we can see the probability scores. In the same way, we can upload any image from the dataset from the test cases and can get the detections, classifications, and the probability score. We can see the application has detected the person, it has detected the bicycle and the bottle. We can see the bounding boxes. We can see the label and we can see the probability scores telling us the confidence level of the application in classifying the detections into that particular class as person, bottle, and bicycle. Click on back. Now we look at the graphs plotted. Click on graphs link here. First, we look at the graphs plotted for Pascal dataset. Click on Pascal here. This is the precision and recall graph of YOLO. This is F1 score graph of YOLO. This is confusion matrix graph. These diagonal boxes are the correct classifications and the remaining boxes are the misclassifications. This is precision scores comparison graph, a horizontal bar graph. In this graph on x-axis, I have precision scores and on y-axis, I have algorithm names. So these are all the algorithms which we have built. So precision measures the proportion of correctly detected objects out of all objects detected. So we can see YOLO V5X6 has outperformed all other models in precision. Similarly, this is recall scores comparison graph. So recall measures the proportion of correctly detected objects out of all actual objects. So we can see YOLO V5X6 is doing well again. And this is MAP scores comparison graph. MAP provides an overall measure of detection accuracy across different object categories. We can see YOLO V5X6 has outperformed again. So these are the graphs plotted for Pascal dataset. Now we'll see the graphs plotted for Udacity dataset. This is precision and recall graph of YOLO. This is F1 score graph. This is confusion metrics graph. This is precision scores comparison graph. This is recall scores comparison graph, and this is MAP scores comparison graph. Now we look at the graphs of cased dataset. This is precision and recall graph of YOLO. This is F1 score graph. This is confusion metric graph. This is the precision score comparison graph. This is recall scores comparison graph. And this is MAP scores comparison graph. So now click on sign out link. So the project successfully developed and evaluated a robust road object detection model for autonomous vehicles using diverse datasets and advanced deep learning techniques like YOLO. With enhanced accuracy and performance, the model contributes to safer roads, improved transportation systems, and increased trust in autonomous driving technology.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.